السلام عليكم أعزائي الطلبة. Today inshallah we'll start with the last part of this course. I'll try to give you, I'll share with you first my slide. Today inshallah the topics on AC motor protection. Can you see the slide?
Yes, we can.
Okay, so what we'll try to show you today, how what I have covered in this course so far, like a few types of protection principles. I have covered the overcurrent protections, directional overcurrent protection, or directional could be power, reverse power protection. I have already covered the differential protection principle and distance protection principles. Today, inshallah, I'll show you how do we other types of protections that are involved in one equipment. Okay, so those can be all or other types of protection that can be utilized to protect one device. One of them is, let's say, a very important component in any electrical systems is the AC motors, and I'll try to show you now the how do we protect AC motors using different types. So first of all, I'll give you introductions. So why do we need protections for motors? So we have to take into considerations motors are utilized in industry for different applications. We use them for pumps, fans or compressors, or we can use them in cranes and conveyors, chillers, which is AC chillers, crushers, so many applications. And based on the failure statistics of these motors, they have estimated the IEEE and EBRI did a reliability survey, and they found that the failure rates is about 3 to 5% per year, and can reach even 12% on some industries like paper industries. So this is a possibility of failures. When they studied those failures, based on this failure, the factory downtime can be very expensive. You know, when you lose some very important motors, it can, for any industry, can leads to cost. Sometimes the cost of losing a motor exceed its cost of motor replacements. The cost would involve replacement and repair, removal, installation, loss of production. And if you add all of this, that's why it might cost a cost of a new motors. And when they did the statistics, and these are two IEEE did one study, EBRI they did another study, and when they tried to classify those statistics, they found, I will give you an average, like they classify the faults into 3 categories, or cause of those failures into 3 categories: electrical related failures, and mechanical related failures, and environmental maintenance, and others. So I like electrical related failures such as overload, like the stator ground, let's say insulation failure, could be core failures, okay, cage, which is the rotor failures, and so forth. Mechanical, so this is the mechanical parts probably like bearings and shaft and okay, and so forth. And for the environmental related could be oil leak or frame or okay, bearing seals, so all of this. So the average of these two studies shows that there is 33, almost one third of those failures is due to electrical related, and some about another third due to a mechanical related, and the third, almost third, due to environmental and maintenance related issues. So we need to know now how do we. So we have to have a proper motor protection is required to minimize those failures rates, and also I would like to prevent damage and ensure both personal safety and production targets. So to achieve the production targets, and it's not only with the protection, we need also monitoring of the motor. So we need we know the healthy status condition of the motor. Now you can interrupt me should you have any question. Now what, as I would, okay, this slide shows the how those hazard or failures are classified. Instead of just showing electrical or mechanical related or environmental, we can even classify them further into motor failures that are induced inside the motors, like insulation motors, whether it is stator winding insulations or the core insulations or the rotor insulations. We have also bearing failures. We have mechanical failures like shaft or due to maybe some damage due to vibration. Okay, so sometimes we have also vibration monitoring devices. Okay, that will trip also the motor when the vibration exceed a limit. For synchronous motor, we have also loss of field. Okay, also have an impact. For load side that's connected to the motor, we have also force related to an overload. If you exceed the rated load of the motors, jamming of the rotor, let's say it's jammed and cannot rotate. We call this a locked rotor condition. It could be a high inertia, so the motor does not accelerate, and we have protection for protection for not to protect motor for not accelerating. You know the motor has a fan at the ends, and those fans, once move, the rotor moves, provide cooling. So if it doesn't reach the rated speed, doesn't accelerate, this also could overheat the winding. It could be also environmental related or induced failures like high ambient temperatures beyond the specified rated temperatures. We could have the area is blocked in the ventilations for the or cold dam ambient temperature. So these could affect also the degree of insulations. We have also source or system that supplies the motor. Okay, also has something related to, for example, we have open phase. One of the phases that supplies the motor is open. Okay, or unbalanced. The voltage supplied to the motor is unbalanced. Okay. So this is from the source supply, power supply to the motor could have an issue. We could have an under voltage or over voltage from the supply. Okay, we have phase reversal. Maybe two phases are reversed, so the motor will move in the other directions. So we have to check that is the motor in the right direction. So we have to check the phase sequence of the motor. Motor could be out of step due to system disturbances. You know, if you have force in the system, also it can lead to a motor, especially if the force can lead, to make the voltage to dip, it can stall, the motor can stall. Even the force, not in the motor, but it's the force outside in the system. We have also operation and application related failures. Maybe sometimes if you try to reclose a motor out of phase. Suppose like induction motors, normally if you, larger ones, if you try to start them and you stop them, or you lose the supply, and before the speed drops to 33%, okay, and you try to energize it again, that may produce a transient currents that's a very high current and is damaging. We have also jogging or repeated start to stop. If you start the motor on off, on off, on off, too frequent, it could be also due to either somebody is operating it in this way. It's not as intended by the manufacturer. That's also can increase the heat. I'll show inshallah in the part of the thermal protection something related to this. So how do we now detect those hazards? Okay, so we need to have different types of protection principles, and these hazards also can be external, due to external force. I say ambulance and the supply. We could use a negative sequence to detect this one, a negative sequence current. Under voltage, I'll use under voltage elements if we have under voltage in the supply, or over voltage. Single phasing, if I lose one phase, I can use a negative sequence current to detect that one of the phases is lost. Reverse phase sequence, if the supply has the two phases are reversed, would change the phase sequence. I can use still also the current as a negative sequence. I can use also the voltage, negative sequence voltage to detect the sequence of the. So these I can check the supply, external faults, okay, in the supply. I could have also for internal faults, I can detect bearing failures by monitoring the heat of the windings or of the sometimes we have bearing or shaft thermal devices, detection devices. We winding force for phase or ground, I can use an overcurrent. We have overload, we use also a thermal type protections, thermal overload protection devices. This as picture shows you failures. This is in the stator winding. This is the location of the failures. So this is the location of the failure due to insulation failures where they have short circuits. And this is a induction motor squirrel cage where we have damage in the rotor, and this is the bearing failures. Okay, so bearing failures, one of the it represents high rate of failures in motors. So regular inspections and those mechanical also would help to reduce those damages. So why do we need a thermal protection? Okay, if you there are two main types of thermal risk for overheated motors. First of all, the insulation uh, of the stator will get damaged, okay? And also, the rotor conductors may decrease their capabilities to resist bending, so it will be a deformed uh, and uh, uh, and even can lead to melting of those rotor winding or parts. And to see like each motor will be the insulation. There is an insulation class for insulation used in the motors, and this will be specified in the nameplate in the of the motor. For example, I'm showing you the standard. These are the curve that shows you of the four classes of insulation. Class A insulation has a rated operating temperature up to 105 degree. It can handle. So it give you, if you operated up to 100% and 105 degree, its life can persist 100%. Now there will be no life loss. For class B, it's rated up to 130 degree, and class F has 155 degree, and class H has 180 degree. So this is like the x-axis is the temperature, and y-axis represent the percentage of life reduction. So percentage of lives. So this is like the aging factor for different class of insulation, motor insulation. From these curves can be clearly observed that a 10-degree increase beyond the rated temperature limit will drop the life to half. Yani, for example, this one, it is rated 105, which is, this is 100, this is 105, give you 100% of its life. But if you increase the temperature 10 degree, which is from 105 to 115, you will see there is a reduction in life is to 50%. So, and that's why thermal protection is very important for motors. I'll show you now how do we provide this now. I will come to this, the thermal protection. So now, what are the factors that we need to know, okay, in order to determine the protection settings for a motor? One of them, and these settings or protection schemes varies depending on various factors, and what types of protection I have to provide depends on different factors. So these are the 5 factors we have to we have to consider, or determines how many protection do we need to provide for the motors. First of the size, the rating of the motor, and the voltage level. The higher the size and higher the voltage will have, more protection functions are required normally. And also the importance, sometimes even smaller motor require larger protection if they are critical for any process. Okay, the importance. We have another also factor is the motor characteristics. We have to know about it. And this is from the manufacturers. And this is one example of motor characteristics, which shows here the starting current characteristic of the motors. So this curve, this is the x-axis, the current, and y-axis is the time in seconds. So when you start a motor, it will draw very high current, okay? And this current is referred to a locked rotor currents, like when the rotor is locked at stationary before you start it, and we try you apply 100 rated voltage, 1 per unit voltage, it will draw this high current. And the current will reduce gradually, okay, until it reaches the steady state, okay, full load current. And this is called the full load amp or motor full load current. So how long does it take to accelerate from standstill to reach the rated speed? This is called the acceleration time. Okay, the time it's required to accelerate to the rated speed. And this varies, depends on the voltage. If you apply lower voltage, it will take longer time to accelerate to reach the rated speed. But the starting current is smaller. That's why we use sometimes starters, starting techniques to reduce starting current by reducing the voltage, but that will increase the time it's required to accelerate to the rated speed. There is another portion, the characteristic called asymmetrical components. This is the steady state, like lock rotor current, but it has also a transient part which decays very quickly. And this transient part, like the three phases, will not be symmetric. It has a decaying DC component, which decays very fast. So these are the, we can get them from the manufacturer. Another important characteristics of the motor that we can provide is the thermal capability curves, which includes the this is related to the temperature. I have insulation temperature. So it includes when the motor is running. This is the thermal capability, means this current, okay, I should not exceed this time, otherwise the insulation can get damaged. Okay, and similarly, this is during the locked rotor conditions, when the motor does not move. Okay, so this is the time at which the motor, suppose you apply 110 volt, it's the rated voltage to the motor, and motor is stalling and didn't move. How long before, how much would we wait before the motor is get damaged? Is this called the permissible lock rotor time, which is this point. There's another factor that you need also to know is the ratio K constant, which is the ratio between the negative sequence resistance of the rotor to its positive sequence resistance. And that is important for, it gives the skin effect. Inshallah, I will come to this later in this presentation. Another factor is the environment, the ambient temperature at which, although let's say these are ratings are provided for this for ambient temperature of 30 degree or 40 degree, but you put it in environment without ventilation or where the environment the ambient temperature can go higher to 50 degree, then there will be a derating effects. So power supply and grounding systems. The type of the grounding systems can affect the ground overcurrent protection that you will use. I'll show inshallah later. Types of the motor starters, because it will reduce the starting currents. So we have different types of starters. transfer starter or rotor resistance starters. We have direct online starters, a different type of starters, which is beyond the scope of this course. What are the fundamental aim of any protections? We have three aims. Okay, first of all, you don't want to trip the motor, okay, um, for any abnormal conditions. I want to operate the motor and permit to operate the motor up to, but not to exceed its thermal and mechanical limits. Mechanical limits related to vibration, maybe, okay, and so forth, um, and uh, and thermal limits related to the overload on and the curves that I thermal capability curve that I've showed you in the previous slide for both overload and abnormal operating conditions. The second, I want to provide maximum sensitivity for fault detections. And third, I want to now, how do we achieve those ones? This can achieve use various types of protection functions. And these are so many protection functions. We have phase over current protections, whether instantaneous or time delayed over current protections, or we have ground over current protections. When I say phase, for protecting windings from phase-to-phase force or three-phase force. For ground force, we have also the 50G or 50N, 51G. And normally G and N related. How do you measure the, I'll show inshallah the difference between these two. Under and over voltage protection, we have current imbalance, we have differential protection, phase sequence, and this is the IEEE code number for those protection functions. We can use RTD, which is resistance temperature device for thermal overload. And thermal overloads, we have this is a measurement, a temperature measurement device. I'll show inshallah later. Thermal overloads protection. We have loss of load or load jam protection, maximum starting and or start per hour or time between start protection. Some motors you cannot start them. If you stop them, you have to wait before you start them again. You have to check the manufacturer. How many starts you can have in an hour? How many maximum time between the starts? So you have to, the protection has to also implement this. We have also phase sequence. Anti-backspin means the motor is not rotating in the backward. Okay, when you stop them, some motors, when you stop them like pumps, it will tend to move in the other direction. Sometimes you don't want to start before motors shafts stand still. Phase sequence protection, but for synchronous motors, we have additional protections. So all of those, the previous I have mentioned, in addition to those, we could have also, in addition to those, for synchronous machine, we would need loss of excitation protection, loss of synchronism or out of step protections, field ground faults protections, because you have a field winding means. So I'll try to go over those one. Before I get this, let's go to the machine theory. See how do we get this lock rotor current, and how the short circuit is calculated, and we bring some insights. So for induction motors, equivalent circuits, you know, you cover this in machines. This is the equivalent circuits. And for a simplified one, this is a simplified version of this, where we added the X represent here the equivalent resistance of the stator and the rotor, and this is represented as XT double prime, direct access subtransient reactance. You know the slip. So for slip, for a positive sequence supply slip, this is the resistance. For a negative sequence supply, this what you will be. So this is the resistance. Now, if you want to find, let's take a typical parameter, see what is the input impedance of the induction motors for different conditions. When it is as a standstill, when you try to apply rated voltage, and the motor shaft is a standstill. So what is its input impedance for the positive and negative sequence? Okay. Also, what was its input impedance when the motor reached its rated speed? Okay. So let's take some parameters, typical parameters for induction motor in per unit of its kVA rating. The resistances and of the stator is 0.01 per unit. This magnetizing inductance is 3 per unit, and X, which is the sum of these two rotor and stator leakage reactances, is 0.15 per unit. And so for at symmetrical lock rotor currents, or we call it the starting current. Starting current is approximated as when S, of course, you know, starting currents when the rotor at standstill, so the slip is 1. And if you try to find it, normally this is very large compared to this. So, and the slip is 1, and resistance is very small, these two. So basically the starting current as a worst case scenario is 1, which is 1 per unit voltage, divided by this, give you the worst case scenario for the starting current. This is called the locked rotor current, about 6 times, okay, for machines of those parameters. Now, from this simplified circuits, we can also calculate the exact input impedance. Now, suppose adding these parameters here, if I take XM barrel with XJX plus R over S for the positive sequence supply voltage, then I added this, I'll get the ZM1, ZM2 is this value of 0.144 angle 87, which is exactly or approximately this value. So this is at stall conditions. Because a stall condition, S is 1 for positive sequence and S is 1 also for negative sequence. So this will be still also R over 1. Here also R over 1. So that's why ZM1 and ZM2, the positive sequence impedance and negative sequence impedance of the induction motor is same at the stalling condition or at the standstill condition. When the motor is running, slip will become very close to 0, and at that conditions, the input impedance becomes this for the positive sequence impedance. We just substituting the parameters here, I'll get this is almost 0.9 or 1 per unit, and for the negative sequence impedance is same as the at standard step. So there is a jump for the positive sequence impedance from change from 0.15 to almost 1 per unit, but the negative sequence impedance did not change, whether as standard still as compared to when the motor running to its rated speed. So this is one observation. Now, how do you calculate the force? Suppose I have a motor now and it's connected to a supply system, and the source impedance of this supply is, let's say, ZS1 or X is source impedance of the positive sequence impedance, and a negative sequence impedance is given, and also I can have also zero sequence impedance, depends on the type of force that I want to analyze. And suppose now we represent those parameters in per unit of the machine base. So what is the base of this machine? Normally you take the input kVA rated power as your base for the machine parameters. How do you find this kVA base for the rated kVA as a base for the motors? Normally you take the HB the horsepower, which represents your output mechanical power, times the 746 watt in this conversion, but 0.7 to change it to kilo, and over efficiency over bar factor gives you the rated kVA of the machines. So most of the parameters of the machine are based on this value if it is given in per unit quantities. And so if I have a system like here, I have a transformer with a source, then you should also represent those parameters in per unit of this, okay? And then I have created a system impedances with respect to the same base. So if I have now, how do you find the lock rotor current? Now, lock rotor current without for an infinite system where the source impedance is 0 is 1 over XD as I showed it here. Right? Now, when you have a source with non-infinite impedance, which is non-infinite source, which have reactance, then it is equivalent as a source impedance plus the motor starting impedance. Okay, that gives you the lock rotor currents. Now, so the lock rotor current will reduce, but because the source impedance is very small compared to the motor resonance, this is approximately 1 over XD double prime. This is the starting current, but the in per unit, because all of these parameters are in per unit, and this is the per unit voltage in per unit. When you have three-phase at the terminals of the motors, three-phase faults, the voltage of the system in per unit divided by XS represents the short circuit level. And because XS1 very small compared to this, the short circuit current will be very, very large compared to the starting current normally. And the third thing is when you have a face-to-face faults, the current will drop to 0.866 of the three-phase value. And assuming here that the positive sequence impedance of the source and negative sequence of the source is same. Now, this gives us a good indication that when we set an overcurrent protection, that I don't want to start the relay, I don't want the relay to operate when the motor is starting. And I showed you here, the starting can reach about 6 times higher, or sometimes even higher than 6 times for some types of motors. So I don't want to because as it's a normal operation, current will start very high, then drops to normal full 1 per unit current at full load. And so, and also I have to say now, there should be a margin between the lock rotor current and the three-phase currents. So this margin gives us a range between which I can choose the pickup setting. So if I want to use an instantaneous relay, then this instantaneous has to be above the lock rotor current and below the minimum fault currents, so that the minimum fault current will be detected, okay, and trip instantaneously. So in this way, normally rule of thumb, we would use the pickup settings is higher than 1.5 to 2 times the lock rotor currents, and 1.5 to 2 to overcome the asymmetric current, which is I showed you here. The current is not exactly, but it has, due to a DC, it has higher current. So that's why I want to have a setting something even above the asymmetrical fault current somewhere here. Okay, and below somewhere to detect the minimum fault, line-to-line faults, I need to take half to 1/3 of this. So I make sure that the relay will operate during a minimum fault current. In some situations, we might not be able to achieve, especially if the fault level is very close to the lock rotor current. The minimum fault current is very close to, which this depends on this system impedance as compared to the total, the motor impedance. So in some situation, if this cannot be achieved, then the 50, if there's no margin between the lock rotor and the minimum short circuit, then the instantaneous resonance cannot be applied. And instead, we can use either time delay instead of, so that the current will decay, or we can, because lock rotor they want to decay, or we can use we can use also other types of protections, like the differential protections, to provide instantaneous setting. So sometimes if you want to have a delay by 0.2 seconds, I can reduce the sensitivity, increase the sensitivity to, instead 1.5 can go to 1.1, 1.2 of the lock rotor current, this one. Okay, but because I have asymmetric current, which is this one, and this asymmetric current very quickly decay, I can set the here my setting in instantaneous, but I have to delay it something few seconds, not sorry, for a few cycles. Normally 10 cycles is enough, which is 0.2 seconds, 0.1 seconds, so 0.2 seconds until this decays. The second thing I would like to explore also what happens if I lose phase. This is an imbalance situation. Okay, and I want to analyze this situation. Now, if we draw the positive sequence for analyzing an open phase, we draw the positive sequence impedance network and negative sequence network and zero sequence network. Normally, motors are not grounded. Normally, if it is a star or delta connected, or even if it stars not grounded. This is a common practice in motors. And because of this, there will be no ground. There will be no zero sequence network will not present. So as a result, I have the positive sequence network, and this represents the machine input impedance, induction motor impedance. positive sequence impedance. This is the source voltage and its source impedance, like I wrote it as XS before. This is ZS of the positive sequence impedance of that source. And this is same without the source, the negative sequence impedance of the source, the negative impedance of the machine. Now suppose a machine I have another parallel load with it, I can also add it here if I have a parallel static load, okay, in it. And we connect these in series, okay, at the fault point. So this is represent now the sequence network to analyze an open phase. Now, if we take the same parameters that given in the previous slides, if I use those parameters, this source is 0.05 per unit. The Z load here as 1 per unit, and Zm already we calculated 0.9 before, and Zm2. So this is Zm1, this is Zm2 is 0.15 per unit. Okay, and we'll try to find the current. So what I want to find the current in the motor, the positive sequence current, and this is negative sequence current of the motor. If I want to find the voltage at the motor, I need to find the positive sequence voltage at the motor and negative sequence voltage at the motor. And we then use this transformation to transform. I don't have zero sequence current in this situation, so I have only positive and negative sequence current from which I can find the phase A, phase B, phase C currents. So let's consider now one scenario, like suppose I don't have any load in parallel with the motors, only motor connected to a source. This is the situation. And I try to substitute those parameters and try to calculate the current. I'll get the current here. All of this becomes a series. Only one parent over the sum of all those impedances gives you the current. And the current will be same in all. So the positive sequence current and negative sequence current will be same, but in opposite direction. Okay, and similarly for the negative sequence, positive and negative sequence current of the motor. And when I substitute those values in here, zero sequence is 0, positive and negative for the motor, we will get that the phase A 0 because it is an open. And phase B will get phase B 1.66 per unit, and phase C is 1.66 per unit. So there'll be a current increase in the other healthy phases due to an open phase. But this increase, now our full load current of the motor is 1 per unit, so an increase about 66%. However, if you want to detect this types of fault using an overcurrent protection, you won't achieve it because normally overcurrent you set at 1.25% pickup, and it is very close. Okay, you don't have enough margin for sensitivity. Okay, for better sensitivity. So instead of using an overcurrent protection, we will use sequence current detection principles. Now, if I look to the sequence current is 0.9, negative sequence current 0.9, almost 1 per unit. So, but in normal operating conditions, the negative sequence current should be not there. So when you have a fault or like an open phase, negative sequence becomes very large. So even if I take 10-20% of the rated value as your pickup, will be good to sense, to detect the negative sequence. So it's much better to use now. Negative sequence to detect like an open phase. We can also detect it using comparison between phases. And if one phase is fully lost and the other has occurrence, so you can use also using imbalance conditions. You compare the current recurrence. If they are different by a very large amount, this is an imbalanced situation, and you can detect this also. Now, how do you choose those elements now that I have mentioned earlier here? Which of these I have to use? Okay, all of them or some of them? All depends on the factors I have mentioned here: the importance of the motor, the kVA rating, the size and voltage level. Okay, so the standard they classified. If you go to the standards of motors, they classified the protection into three categories. Protecting a low voltage motor, a low power motor, up to 100 horsepower. So this is normally low voltage system. And when I say low voltage, is below 600 volt, below 1000 volt, okay, as per standard. Now, for those motors, normally, because they are smaller and not costly, so you don't provide sophisticated protection system. Mostly motors, low voltage and less than 100 HP are protected by thermal overload relay and a fuse, or a thermal overload relay and a breaker, a circuit, a low voltage breaker. And now this low voltage breaker is not the breaker that we have covered, which is a mechanical device that need a command from a relay to operate. It has also integrated protection thermal, like instantaneous elements, like a fuse operate instantaneously when there is a fault in the motor. And we have also contactor. So we have three elements. We have a fuse or a breaker to detect short circuit, for short circuit protections, whether it is face-to-face fault or ground faults or three-phase faults. So you want to provide fast-acting operation to clear the faults. The thermal overload provides the protection for an overload conditions, so that you don't exceed the thermal limit. And the contactor here is used as a switching device. Okay, so contactor are used in industry to switch on off circuits like motors. So if you look to the pictures here, this is the contactors and this is the overload relay. And they can be attached or detached. And here I didn't show the breaker or the fuse, which is before. Now, we have to, do you know what's the difference between a contactor and a switch? And Shabab?
وإيش الفرق ما بينهم دكتور؟
Okay, now what's the difference between a circuit breaker, a contactor, and a switch? Okay, so a switch normally you switch on off manually, okay? But a contactor, I can switch on off a load, okay, using a low voltage, a lower voltage, remotely or locally. Because this is one thing. It allows remote control of a voltage of a circuit, or also designed to handle thousands of switching. Let's say a contactor are designed to be switched on 1 million times during its lifetime, while circuit breakers are not designed for such. يعني I cannot, although a circuit breaker uses for switch on off, but their as per design, circuit breakers are not designed for frequent switching. Okay, low voltage circuit breakers. Third يعني difference here. Now here we want to switch a conductor, use a lower voltage to switch it on, as I will show inshallah in the later in another slide. The conductors have additional contacts where I can provide indication of the status of the motor is on or off. We call them auxiliary contacts. Some of them is here, some of them normally open, some of them normally close. I'll show how do you use these ones. So a conductor is basically a coil and a contact. So if I want to draw it, it is like this is a core. Like E-shaped core. And in that E-shaped core, the lower one is fixed, the upper one is moving. And it's moving, the upper one moving with contacts. So the contacts here, so this contact, this is a bar. So this contact moves with this upper ones. Now I have a coil here, wound. And this voltage can be low volt normally. It's either, let's say, it could be 220 volt or 240 volt, could be a 24 volt, which is safe to switch on of low voltage contactors. So this is the control voltage to switch on contactor or switch off contactors. So the contacts have several, the contactor here has several, on the top one has several contacts which moves with the upper one, move up and down with the upper ones. So let's say some of them is normally open, like this one. If I put another one here. So this is normally open contacts. So if you energize this upper core will be attracted to this. So, and I have a spring also here. So when spring will make this is the contacts is open. So when you energize this will be pulled down. Okay, this will be closed. So this contacts will be closed and the current can flow here. No, so for three-phase contacts, I have three main contacts, which is now, this is phase A, for phase B and phase C. And I have also additional auxiliary contacts, which also some of them are normally closed, and when you energize, this becomes open. This is the basic construction principles of most of contactors. The problem here is of contactors also, they have limited breaking capacities. يعني, you cannot break any fault currents, like a circuit breakers, also designed with the limited break capacities. So the contactor is normally designed to break up to 10 times its rated current. And now if the fault current is more than 10 times rated current and the thermal load, sorry, and you don't have, let's say, a fuse here, and you just relied on thermal overload, and the thermal overload will trip the circuit, the contactor. So in this case, the contactor will get damaged because for short circuit current will be higher than the breaking capacity of the contactors, and the contactor will get damaged. And because of this, we provide a fuse. A fuse will blow, okay, uh, to and open the circuit before contactor gets get damaged. Or we use a circuit breaker. So we trip short circuit by the circuit breaker, not through the contactors. If you want to trip through the contactors, you should make sure that the contactor breaking capacity is higher than the maximum short circuit level. Okay, and this contactor can be used from 600 volt to 6.6 kV volt motors. We can switch them using contactors. But normally motors at higher voltage like 11 kV, we use circuit breaker. We don't use contactors for switching. Okay. Circuit breaker is same as we mentioned in this course. This is the first classification of group as per standard. This is what mostly low voltage you will see in industry motors are protected in this way. And for the other category, like from up to 1000 HP, you need additional. So you need a circuit breaker now. This is 52 in a state of a contactor. I need to have additional protections, like I provide the thermal in a state of thermal relay. Okay, we have protection elements, the 49, which is a thermal overload protection element. We have the 46. We have also 50 and 51 for short circuit protections. And we have ground fault protection, which is connected to a CT. This is core balance CT. I don't know if you can remember from the CT part, core balance CT for, so all the three-phase wire pass through the core, okay? So this is the core of the CT, the three wires pass through. This is core balance CT, and this is used for ground fault detection. So now 50G, when you use a core balance CT, 50N, okay, when I say 50N, normally you calculate the current by summing the three by using the neutral connections. I'll show inshallah later what's 50G and 50N. Also, I need the 46 and 47. 46 for the imbalance. This is imbalance protection. Imbalance protections. So imbalance, this is, we have two types of devices we use for imbalance, the 46 for current imbalance and the 47 for voltage imbalance, okay, devices. And this is like, as I mentioned, based on negative sequence current, I will be able to know if I have lost a phase or there is a certain voltage imbalance, or if the phases are also changed, okay? All I can use this through, detected by through this elements. So this is like a second level where these are required. Now, this is a larger motor, more protection is required. For more than 1000, you need additional, you need a differential protection, okay, added. You need, in addition to the previous one, you add a differential protection. In addition to the if you have a synchronous motor, you need also to have a field winding protection, loss of excitation. I have also under voltage and frequency, high or low, over and under frequency protection, low power factor protection, out of step protections are added if you have a synchronous machine. This is for a synchronous machine, which shows the protection elements. Okay. This is for the rotor field protection. Now how these are connected. This is like from a commercial relay. I took it from a standard relay in GE for low voltage motor control centers. When I say motor control centers, means when you connect more than one motor from one bus. Okay, so there is one control panel that feeds all the motors. Now, from this G manufacturer for low voltage system, the standard, which is already built in function in those relays, is you have the 49 and 51. This is overload for overload protection, 49, and this is like time over current. This is the thermal overload protection, and 46 for phase imbalance, for current imbalance, for loss of phase. Okay, and you can have another option of adding also other 50G and 51G through a core balance CT, and we have lock rotor or stall protection. We have hot. This is RTDS, RTD. RTDs are thermistors, or we call it resistive temperature detectors or devices. Those are designed to measure the winding or shaft temperature. So winding temperature are sensors to sense directly the temperature of the winding. Based on this, we know the status, the local temperature of the winding. And we can trip or alarm based on this temperature if we exceeded the limit. We have under current or under power protection, under voltage and over voltage protection. And this is how you connect the CTs. So this is like a fuse with the contactors, and these are the VT and the CT. Okay, VT is required because you have an under voltage and over voltage elements, and we have also the under voltage and over voltage elements. We can, from the voltage also, we can check also if we have phase and we can measure the frequency or measure. Okay, I can identify the sequence also of the supply. And this is how the CTs looks like. So for this CT, core balance CT is this. This is the core balance CT. So all the three phases pass through the core, through the opening of the CT, is connected to input channel for the ground over current protection. And the three CTs are connected as for one for each channel. Okay, and this is the VT input here. I have just line-to-line voltage connected here. In this case, I will not be able to detect. I can use only under voltage, over voltage, but I cannot detect the sequence, because for sequence I need the three phases. Okay, so I can detect sequence from the current, the phase sequence, or the imbalance conditions. Uh, these relays, which is dedicated for motor, I can start and stop them. The motor can be used to be started from the relay. Relay, if you start and stop, give a command to the relay to can start and stop the switch on or switch off the contactors through the relay. Also, you can start it remotely in a control room. I can know the indications of what is the status of the motor is on or off. I can also remotely start or stop this motors. Okay, so can be switch on or off, switch off locally or remotely from a control room. This is another slide that shows for medium voltage and high voltage motor, you need additional protection. Uh, you need maybe RTDs, temperature sensor on the bearings, okay, in addition on the motors. You need to measure sometimes the ambient temperature, the intake, okay. I can measure the stator winding RTDs. We have additional protection as I mentioned before. And these are, I can add differential now here. I can have differential protection, directional protections. Now we have, this is the motor connected as a star. We have CTs at the before the star point and CTs at the beginning of the terminals. Okay, and this is because I need to implement a differential protection, so I need to have. In addition, I can have an overcurrent protection through this CTs, and this is the core balance CT, which is dedicated for ground fault protection. And this is the circuit breaker now, okay? And these are the three VTs, so it's connected as a star, and I need them sometimes to detect also under voltage or over voltage, or checking the sequence, if I lost a phase or not. Now, differential protection can be also implemented using this technique. I will come to this, that the two wires of each phase is passed through a CT. Okay. So this is another way of implementing differential protection for motors. For motor control, to control the closing or of a contactor, so this is what I tried to show you before, I mentioned before. Now, this contactors is the normally open contacts. So at normal operating condition, when you didn't energize the coil of the contactor, this is represent the coil of the contactor that I have drawn here. So this is the coil. If you apply a voltage here, this will be energized, the contactor coil M. And normally this contactor, in a contactor, the terminals of conductor normally A1 and A2. And to know where are the terminals of this coil, this is normally in standard. The terminals أطراف الcoil A1 and A2 are the terminals. So if you energize this A1 and A2 with a voltage, this contacts will close and supply the voltage to the motor to start. So how do I do this? Now, suppose this coil of the contactor is require, let's say 24 volt. I need a voltage to be stepped down to 24 volt. If it starts at 110, I need to step it down to 110. So it depends, you have to check the contactor. This is what's the operating voltage for this contactor to control is open. So where is A1 and A2? This is A1 and this is A2 of the contactor. Okay, now if you energize this, will be closed. How do I energize it? So I will take the line, okay, to a start push button, to then to a stop push buttons in series. Then, so when I close this start, there's a voltage will be applied to the conductors, so the conductor will be closed. And at the same time, I can use auxiliary contactor. This is another contacts from the conductors, which is at the top, which is one of the auxiliary contacts, normally open contacts. Okay, uh, so normally open contacts, I will connect it in parallel with the start uh, push buttons. So already once this is started, this will be energized. Also, this will be closed, and this all the closed, so current will flow. And once I release my hand, the current will flow now through this bypass contact and continue. So when there is, you want to stop it, I will disconnect the supply from the coil by opening this. So this all will be open. In addition to this becomes open, so the current will not flow anymore because this becomes open and this is already open, okay? Uh, and this de-energized, so this becomes open, so the motor stops. Now the overload contacts. Now in the overload, I have also contacts here. Um, so these are the contacts, which is there's a contacts, yeah, here down here you have contacts. This is for output to the motor. This is supply input, and here there are contacts dedicated for this. Now when this is strips operate, so the normally closed contact becomes open. So normally you have only for the three phase we have only one contact rather than three. So one of them is normally during normal operating conditions, this is normally closed. So when there is an overload, this becomes open. Once open, it will mean disconnect the motor due to an overload conditions, and the contactors becomes disconnected. Sorry, the motor will be disconnected from the supply. Now, if we use relays, and the problem with these conductors, the voltage dips, okay, to below, let's say 70%, or sometimes it depends on the conductors. This conductor will de-energize and open. To avoid this, that you don't want for because of any drip in voltage contactors open, we want to control it, we have to supply the coil through a UPS system. So the voltage here will not be affected by faults or whatsoever, okay, or drop in voltage. So this is called the electrically held conductor will under voltage ride through. And also same principles here, I can control the closing and opening of the contactors of the circuit breaker instead of a contactor. If you use high voltage motors above, let's say 1000 HP, I would use, let's say, a contact as shown here, or even 1000, I'll use circuit breakers. And now I can close and open the conductor through, the circuit breaker through the relay. Now I'll go over each. This is how we control the switching of a motor now. How do we protect those now? How do we set an overcurrent or thermal overload or negative sequence elements and so forth? Do you have any questions so far?
لا دكتور, no questions.
Okay. What's the time now? Let me check. Just stop me, remind me because I don't see the watch, and just let me know if I reach the time. Now, what are these protections? Phase of them is phase over current protection principles. Uh, we use them to detect the short circuits. We know the short circuit, as I showed before, is normally higher than the starting lock rotor current, and however, so we can use this towards our benefit to detect short circuits from lock rotor conditions. Um, we can also, we know that the phase over current devices detects mostly phase-to-phase faults and also three-phase faults. So we have phase over current protection and ground over current protection that I will show you later in the next slide. So the phase over current protections detects phase-to-phase and three-phase faults conditions. Now, failure to detect such faults will result on an increase in motor, conductors, or feeder cable damage, and due to high current, stator iron also or core will get damaged. Okay, and we will have a prolonged system voltage dip due to short circuits. That also can lead to some motor in the system can also stall if you have a very long system voltage dip. And how do we set those setting? As I mentioned the previous, our setting of I would use instantaneous relays to detect short circuits. The setting has to be greater than the lock rotor current. This is the lock rotor current, but even higher than the asymmetrical uh, uh, lock rotor current, which is starting current with the decaying DC component. Okay, uh, and also it should be lower than minimum fault current. Suppose this is the minimum fault current, which is phase-to-phase fault currents. So our setting has to be greater than this and below this, greater than normally asymmetrical. So to be greater than symmetrical, we use a factor of 1.65 to 2 times electron. This is called high set stage 1, stage 2, high set 2, or sometimes they call stage 2 level. So this is instantaneous. There is no time delay on this. Why? This is the setting. This value, a pickup setting here is 1.65 to 1 point times lock rotor current. So what, this 1.6 will guarantee to us that we have exceeded the asymmetrical, okay, current. So there is no, if you keep it closer and make it instantaneous, if you put the setting here, it will always trip. The motor will trip at starting. So this is the high set. This one is very fast. But if you choose this setting beyond the minimum, you will not detect the minimum fault current, but you will detect, let's say, three-phase fault currents. So this is the first setting. Second, you can have sometimes a more sensitive settings, but you have to delay it. I can still go closer to the lock rotor current by higher than by 20 to 50%, 1.2, sometimes we use to 1.1 to 1.2%. It depends on also the relay type. Some relays can remove this, like numerical relay can remove this from the starting current. Then I can go even to 1.2 or 1.1, okay? But if your relay doesn't remove remove the asymmetrical fault current from the measured current, then I can go to a safer to 1.5. So as you can see here, but because of this, it has a symmetrical current. You put my setting here where I have a starting current here. I need to wait for this starting current or asymmetrical starting current to decay. So I need to wait up to here. So this time setting has to be greater than the starting asymmetrical current time. So normally this is to 6 to 10 cycles, or let's say if it is 10 cycle of 60 hertz, okay, or 10 cycle of 50 hertz, okay. So that's about 1/5, okay, or so about 0.2 seconds time. Sorry, lower 0.02 seconds. So 10 cycles is enough. So this is the time here. Settings. So this is like now for detecting short circuits. Now, if any current higher than this is just because of a short circuit. It's not due to a starting. All right. Now, suppose the short circuit level is too close to the starting currents. For larger motor, okay, the starting current can even reach closer. Or depends on the system. This fault level here is closer to the starting current. You cannot use an instantaneous if you don't have enough margin between the lock rotor current and the minimum fault current. In that situation, we'll use a differential instead as a solution. To detect, let's say, short circuit current, short circuit conditions, and act instantaneously. For ground fault protections, the 50 and 50, 50G and 50N, so this is all fault that involve ground, okay, with motor windings. So faults, failure to clear those faults also result on the same damage that I have mentioned. Settings depends on the ground design system now, because here now, as I said in the beginning, the grounding system affects the settings, and this is what I'll show now. There are three types of grounding systems. So the grounded systems, normally this is typical for a low voltage system. Normally ground faults can reach the phase faults, like high current. And now we can use easily, we can use even fuses would acts with this, detects this. But for low resistance grounded systems, um, and those systems normally they will limit, we put resistances to limit the ground fault current to, let's say, 100 ampere to 1000 ampere. And fault normally is allowed to be clear within 10 seconds. And for high resistance grounded systems, the fault level is less than 10 ampere, and that's why sometimes it's difficult to here is difficult to, sometimes you need very careful how do you set the current pickup setting, so the fault current is not too high, it's too low. This is the primary current, it's not the secondary current. Now if you low solidly or low resistance grounded system, normally your pickup for the ground over current relay should be lower than the minimum ground faults level. Normally we take 1/3, this is a general thumb. 1/3 your pickup settings, 1/3 of your ground line to ground fault level. Or you can take from 40% to 60% of your full load currents. As I mentioned, because for low grounding system, the current is high, okay? So we use 40% of your full load is enough. And for a time delay, we delay 2.2 seconds in order to ride through the false residual, false asymmetrical currents. Okay. Uh, for high resistance grounding systems, normally we use alarm. We don't trip on because it's very already the current is very low. And we use normally a core balance CT rather than we connect three CTs. So here it has a must now to use uh, this CTs to detect for ground fault protections for high, especially for high impedance. And now this is summary of the settings for solidly grounded systems. Um, this is the settings level, and this is the time settings. Now can use like here definite time over current protection. It's like instantaneous with a time delay. So that's why it is called 50. It's instantaneous with a short time delay. And so what's the difference between 50G and 50N? Now 50G, when you connect, I don't know if I have this here. If you connect the CTs, the three CTs of the phase CTs in, uh, in these to each channel, and then and you take the, I don't know if I see, and from that, let me check if I have a slide here that shows.
دكتور السموحة منك بس وصلنا الساعة 10 دكتور.
Okay, I will stop. Okay, in a minute. Okay, so the ground relay 50 N. This is the 50 N where I take the summation of the three CTs currents and input to the ground for ground over current protections. But the 50G, when you use a core balanced CT, this is a core. All the three phases pass through the core of the CT, and this goes to the relay. This is so 50G and 50N. 50N, when you use that neutral, the three relays of the star point of the three relays goes to this. This is for conventional fuse numerical relay. This is how you connected what I showed you. So inshallah in the next class, if I have another, I will show you now how do we, in part 2, inshallah after Eid, how do you set also other types of protection principles. I'll stop at this slide and continue inshallah at a later.